Welcome to the Highway Capacity Software video for the Missouri Department of Transportation. This video corresponds with the MoDOT Engineering Policy Guide 905.3.5.2.1. One of the available analysis tools commonly used by MoDOT is the Highway Capacity Software, or HCS. HCS is a traffic analysis software package that contains a series of modules: streets, stops, roundabouts, highways, and freeways that can implement and analyze the procedures and methodologies outlined in the Highway Capacity Manual, or HCM. This video will review each of these modules and discuss the capabilities, strengths, and limitations of the Highway Capacity Software version 7, which implements the methodologies from the 6th edition of the HCM. Then, we will discuss several types of reliability analyses that HCS can perform. Additionally, a checklist has been included in the EPG for those reviewing HCS modules. For those wanting to learn more about how to use the software in detail, please refer to EPG 905.3.5.2.1. You should walk away from this video knowing the capabilities of the HCS, as well as its strengths and limitations. HCS is a deterministic traffic analysis software package that can be used to analyze streets, stop-controlled intersections, roundabouts, highways, and freeways. Deterministic models use static formulas to determine relationships of flow, speed, and density of the traffic stream. Those models are ideal for analyzing isolated or small-scale facilities and freeway or highway facility segments. HCS is a widely accepted tool that can be quickly and easily used with simple parameters and inputs. The software's strengths include the ability to quickly predict capacity, density, speed, delay, and queuing, as well as the ability to perform a multi-hour peak period analysis. HCS uses standard HCM traffic data parameters and inputs, including but not limited to traffic, geometric data, adjustment factors, and demand data. Other HCS strengths include the software's ability to perform reliability and work zone analyses. A key limitation includes the lack of ability to analyze network or system effects on travel flow. For example, individual HCS segments do not account for upstream or downstream congestion or bottlenecks, but can only analyze isolated segments one by one. Also, since HCS is limited to the deterministic methodologies of HCM, it is strictly equation-based and compared to microsimulation has only a limited ability to analyze oversaturated conditions where queues dynamically interact between closely spaced network elements such as ramps and intersections. The strengths and limitations of HCS should be considered when determining an appropriate analysis tool. It is important to note that the freeway and reliability modules are covered in detail in this training video because of the benefit of using HCS for those modules relative to other modules. For example, synchro is sometimes used for signalized intersections, but HCS is chosen over synchro to analyze freeways. As mentioned earlier, HCS consists of a series of modules: streets, roundabouts, highways, freeways, and multiple reliability analysis modules. The streets module within HCS can analyze signalized intersections. An intersection's demand, phasing, and timing attributes are input into this module to calculate volume to capacity, delay, queuing, and other key MOE outputs using HCM methodologies. The module also provides the ability to optimize a signalized intersection. While this option is available in HCS, MoDOT typically uses Synchro to analyze signalized intersections. The stop module within HCS can analyze two-way stop control and all-way stop control intersections. These modules are ideal for analyzing isolated stop control intersections by lane group and approach. For congested conditions and for closely spaced intersections with upstream and downstream signals, it is recommended that microsimulation models be used to account for the influences of queuing. The stop modules allow for no more than 4 approaches to be input and for no more than 3 lanes on each approach. While this option is available in HCS, MoDOT typically uses Synchro to analyze stop-controlled intersections. HCS also has a roundabout module for analyzing roundabout intersections. Though MoDOT typically uses SIDRA to analyze roundabouts, the use of HCS may be considered for preliminary course analysis. Note that the roundabout module is limited to 1 or 2 lane entries and single bypass lanes. It is also limited to no more than 2 circulating lanes and no more than 4 approaches. The highway module works for 2-lane and multi-lane highways. HCS highway analysis applies to uninterrupted flow segments of highway that are more than 2 miles from the nearest point of fixed operations. The highway analysis facility types are 2-lane, meaning 1 lane in each direction and typically rural, and multi-lane, meaning 2 to 3 lanes in each direction. Examples of data inputs in the highways module include segment length, traffic volume, lane width, speed limit, passing allowance, grade percent, pavement condition rating, shoulder width, and access points per mile. HCS freeway analysis is performed through segmentation due to the static, equation-based analysis limitations of HCM. Segments are broken into the following facility types: basic freeway, merge-diverge ramp, and weaving. Each freeway segment is established by boundaries or influence areas. As shown in this diagram, merge ramps have an influence area of 1,500 feet downstream from the physical gore, and diverge ramps have an influence area length of 1,500 feet upstream from the physical gore. Weaving segments have an influence area of up to 3,000 feet between each physical gore, plus 500 feet upstream and downstream from each physical gore. Basic freeway segments typically fall between the influence areas of merge-diverge or weaving segments. However, basic freeway segments can also have boundaries established by changes in traffic characteristics or geometrics, such as changes in number of lanes, lane or shoulder width, grade percentage, terrain type, or posted speed. As a deterministic analysis software, the Freeways module can quickly provide analysis results with minimal data requirements, making it one of the more applicable HCS modules with the ability to efficiently evaluate multiple scenarios during the alternatives analysis. Particularly, since the other freeway analysis software option would be a time-intensive, data-heavy simulation tool such as Vissim or Transmodeler. Information on the level of service, or LOS, calculations, and determinations can be found in Chapter 12 through 14 of the HCM version 6. The HCS Freeways Facility Module is recommended when studying a freeway corridor. It analyzes a freeway facility by linking the analysis segments of basic freeway, merge-diverge, and weaving into a single interface. Jam density and Q discharge values are applied to the string of analysis segments to determine potential bottleneck locations and adjust the capacity of adjacent upstream analysis segments to simulate the effects of queuing. Due to the static limitations of HCS, it is recommended to consider using microsimulation software such as VISM to analyze oversaturated scenarios along freeway facilities with dynamic queuing interactions, but it is a good way to look at an undersaturated freeway corridor over multiple time intervals. The Freeway module can apply certain parameters globally to the facility. The facility is segmented into traditional basic, merge-diverge, and weave freeway segments as in the Freeways module. The overlap segment is introduced in the facility module. An overlap segment is used when the following three criteria are met. A merge segment is followed by a diverge segment. The ramp gores are 1,500 feet to 3,000 feet apart, and there is no continuous auxiliary lane between ramps, which would classify it as a weave. The facility can be automatically segmented by using the segmentation button found at the top of the Segments tab. This allows the user to enter basic information like the presence of on and off ramps, the distances between them, and the number of lanes. The number is then used to automatically segment the facility into basic, merge-diverge, weave, and overlap segments. It should be noted that facility planning is based off HCM Chapter 25, Section 6, and has fewer data requirements than the facility module. It is intended for a higher level analysis. There are a variety of unique cases that can occur in the analysis of freeway segments. As a rule of thumb, it is always best to review the HCM to see if the unique situation is directly addressed. If not, subdivide the segment of concern into multiple segments for analysis. Common special cases include, but are not limited to, weaving segments that exceed the weaving maximum length, acceleration or deceleration lanes longer than 1,500 feet, back-to-back merge-diverge segments less than 1,500 feet apart, or taper exit only. Pause the video here to read the tips shown on your screen for addressing each of the common special cases of freeway segmentation. There are several types of reliability analyses that HCS can perform. FHWA defines travel time reliability, or TTR, as the consistency or dependability in travel times, as measured from day to day and across different times of the day. Conventional capacity analysis methods evaluate average weekday peak period traffic operations. Generally, commuters do not experience average travel conditions on any given day. Rather, they experience a range of travel times. Improving travel time consistency can improve user perspective of operations even if the average travel time does not decrease. A paradigm shift from capacity addition to capacity efficiency is occurring as congestion continues to grow amid limited resources to add capacity. Travel time reliability analysis focuses on the influence factors on variability of travel times, demand fluctuations, weather events, incidents, work zones, and special demand events. The only variable in density delay-based analyses is demand. However, travel times can fluctuate even on a facility with consistent weekday peak period demand levels. Analytical methods of TTR use existing data sources to evaluate facility reliability based on historical data. Predictive methods use variable distributions calculated from historical data to predict the future reliability of a facility. For the first time, the HCM 6th edition includes a predictive method to evaluate TTR. Dedicated chapters for both freeway reliability and urban street reliability, chapters 11 and 17 respectively, provide a methodology to implement predictive TTR analysis as an extension of existing freeway facility and signalized corridor analysis methodology. HCS 7 implemented the new methods via new modules, facility reliability and streets reliability, that use freeway facility and streets as a base model to be analyzed for reliability. With regards to predictive reliability analysis, HCS generates at least one 24-hour scenario for every month and day of week combination. Influencing events are applied to each scenario to generate a sample of travel times over a specified period, typically 1 year. These events are assigned to scenarios based on default event distributions applied directly by or modified by the analyst to reflect local data. The flowchart on your screen is a high-level overview of the reliability methodology. Speed, demand, and capacity adjustment factors are used to adjust the predicted travel time of each scenario to account for occurrence of influencing factor events. Once scenario travel times have been adjusted, the output of the HCS reliability modules are derived from the cumulative density function of scenario travel times and travel time probability distribution function plots. Freeway reliability builds upon predictive reliability analysis. Deterministic analysis of a sequence of HCM segments, think basic, diverging, merging, and weaving, as an entire freeway facility was introduced in HCM 2010 and expanded in HCM 6. The HCS 7 Freeway Reliability Module inherits facility analysis parameters from the Freeway Facilities file on which it is based. Segment data, base demand data, and analysis parameters can only be modified in the underlying facilities file and re-imported into the Freeway Reliability Module. Influencing variables used in the analysis can be modified by the analyst to tailor the study to the project. Individual demand scenarios, such as month or day of week combinations, can be repeated several times to increase the sample size of stochastic influencing events. Influencing variables and events include weather events, demand data, incident data, work zone data, and special events. For example, adverse weather events may negatively and directly affect travel times by forcing drivers to reduce their speed or indirectly by increasing incidents. HCS considers rain, snow, severe cold, visibility, and non-severe weather. A nationwide default monthly weather event distribution is built into HCS, as are monthly weather event distributions for approximately 100 cities in the U.S. HCS includes built-in weather event data for several regions within or near Missouri, including Kansas City and St. Louis. Incidents such as crashes and disabled vehicles are events along the roadway that impact the rest of the traffic stream. If sufficient incident data is available, a frequency rate can be calculated and directly input into the module. In the event no data is available or the facility being analyzed is proposed new construction, the Highway Economic Requirements System crash rate model can be used with an incident to crash ratio to estimate the incident frequency per 100 million VMT. Known work zones can be explicitly added to reliability analysis. Section 616.25 of the MoDOT Engineering Policy Guide includes anticipated work zone capacity reductions. The special event component of the reliability methodology is primarily used to exclude from the travel time reliability analysis day or time periods impacted by an abnormal event such as concerts, sporting events, or fairs with traffic far in excess of normal peak period conditions. HCS includes a dedicated module to implement the urban streets reliability methodology included in HCM. The urban street methodology analyzes signalized arterial corridors with multiple signalized intersections. Many of the travel time reliability concepts presented in the freeway reliability section are applied to the streets methodology. However, there are some parameters unique to the streets reliability methodology. Like the freeway reliability methodology, weather data for many U.S. cities is preloaded into the HCS Streets Reliability Module, including Kansas City, St. Louis, Columbia, and Springfield. Weather metrics utilized for the streets methodology are different from the freeway reliability module in that streets includes a parameter to account for the length of pavement runoff after a snow event and demand factors for dry weather, rain events, and snow events. HCS Streets provides three functional classes: expressway, principal arterial, and minor arterial. Default hourly demand ratios are provided for weekdays and weekends. Local data can be used if available for all demand ratios. Streets reliability incident data differs from most of the freeway reliability modules among the input components. An annual average crash frequency is specified for all intersections and segments comprising the streets network. A table of default clearance times is based on the street location, event type, lane location, and severity for various weather conditions. Another table provides a default distribution for all of the combinations included in the clearance timetable and proportions for each category individually. Unlike traditional density or delay-based measures of effectiveness that use a level of service scale, travel time reliability utilizes a set of measures to tailor output to the specific analysis. These graphics show the probability that a roadway segment density or speed will fall within a specific range. For this example, the density will fall within the level of service B range and speeds will be greater than 60 miles per hour the majority of the time. Changes in travel times resulting from operational level improvements are best reflected by 80th percentile travel times. The 95th percentile travel time is commonly referred to as the planning time, the time most commuters allow to achieve an acceptable on-time arrival rate. Graphical plots on the travel time index distribution, as shown here, can also provide a visual indicator and comparison of travel time reliability. Most travel time reliability metrics are based on the Travel Time Index, or TTI. TTI is calculated by dividing the scenario travel time by the base free flow travel time. Travel Time Index is preferred over the actual travel times because it allows for comparisons between facilities of different lengths. This table lists several common travel time reliability metrics reported in the Travel Time Reliability modules of HCS. HCS reports percentiles in Travel Time Index along with the base free flow travel time imported from the base sheets file. The last step in the HCS process is reviewing the HCS checklist. Every HCS model submitted to MoDOT will be reviewed by a member of MoDOT staff using MoDOT's HCS Model Reviewers Checklist. To encourage agencies and consultants to review their work prior to submitting, this checklist has been made publicly available in EPG 905.3.5.6. The items in this checklist accompany EPG 905.3.5.2.1. Modelers and reviewers should refer to this section if they need clarification on MoDOT's best practices regarding HCS. When using this checklist to review a model, a mark in the check column by the reviewer indicates acceptable items. A mark in the NA column indicates that the item does not apply to the model being reviewed. If an item applies to the model being reviewed but is deemed unacceptable or in need of adjustment, both check boxes for that item should be left blank, and the reviewer should address the issues with that item in their comments at the end of the checklist. There are several resources available to you as you use HCS. EPG 905.3.5.2.1 and the HCM contain an abundance of information about using HCS as an analysis tool. You can locate the MoDOT TIA Guidance Manual at EPG 905.3. Time to see what you've learned. Question 1. Which is considered a key strength of the HCS software? A. Uses simple parameters and inputs. B. Ability to quickly predict MOEs. C. Multiple scenarios can be evaluated much quicker than with simulation software such as VISM. Or D. All of the above. The correct answer is D. All of the above. Question 2. True or false? HCS 7 does not have the ability to analyze oversaturated conditions where queues dynamically interact between closely spaced network elements such as ramps and intersections. This answer is true. Question 3. Which HCS module is recommended when studying a freeway corridor? A. Streets. B. Highways multi-lane. C. Freeways merge. Or D. Freeways facility. The correct answer is D. Freeways facility. Thank you for watching this video. Other videos are available on multiple TIA guidance topics. If you have any questions, please reach out to MoDOT Central Office Highway Safety and Traffic.